A floating platform anchored in open ocean faces wave forces that can exceed 20,000 tons per square meter during a storm. Engineers designing the first generation of floating cities discovered that the ocean doesn't care about your blueprint. The promise sounded straightforward. Build modular platforms that float on the surface, connect them into neighborhoods, and solve land scarcity in coastal nations facing rising seas. Proponents compared ocean colonization to space settlement, calling the sea a proving ground for humanity's next frontier. Unlike land reclamation projects such as Palm Jumeirah in Dubai, which moved 94 million cubic meters of sand to create fixed artificial islands, floating structures would ride with the water rather than fight it. The concept attracted serious investment. Japan's Ocean Spiral City proposal carried a price tag of $26 billion and aimed to house 5,000 people by 2030 using a hybrid approach with submerged modules tethered to platforms above. But open ocean is not a calm harbor. The first constraint emerged from wave dynamics. A platform rigid enough to support buildings becomes a target for destructive interference patterns. When swells arrive from multiple directions, they don't average out, they stack. A 6-meter wave hitting a 12-meter wave doesn't create 9 meters of displacement. It creates 18, and the force transfers directly into whatever structure interrupts the water. Early floating city prototypes designed for sheltered bays performed adequately in computer models. The same designs, placed in actual ocean conditions, experienced structural failures within months of deployment. Welds cracked, joints separated, entire pontoons flooded, because the engineering assumed wave action would behave predictably. The second constraint was anchoring. A floating platform doesn't stay in one place without active resistance. Developers initially proposed mooring systems similar to those used for offshore oil rigs, with tensioned cables running to the seabed. This works in water depths up to 300 meters. Beyond that, the cable weight becomes unmanageable, and dynamic positioning systems that use thrusters to counteract drift consume fuel at rates incompatible with residential budgets. Ocean Spiral City's design included a vertical shaft extending 1,500 meters to the ocean floor, but construction challenges for such a tether in open water remain unresolved. Without reliable anchoring, a floating city drifts, and a drifting city cannot maintain utility connections, shipping access, or legal jurisdiction. The first major attempt to address these constraints came from modular flexibility. Instead of building one massive platform, engineers proposed networks of smaller hexagonal units, each independently buoyant and connected by flexible joints. The theory held that articulated structures would conform to wave motion rather than resist it, distributing stress across multiple connection points. A Dutch consortium tested this approach in the North Sea in the early 2020s, deploying a 12-unit prototype. The modules survived moderate weather, but the flexible joints introduced a different problem. Residents reported constant low-frequency motion sickness. The platform moved correctly from an engineering standpoint, but created an environment humans couldn't tolerate for extended periods. Buildings swayed. Walkways between modules flexed unpredictably. The project demonstrated that surviving the ocean and creating livable space are not the same achievement. The turning point came when engineers stopped trying to make floating cities behave like land. The breakthrough was semi-submersible architecture. Instead of floating on the surface, where wave energy concentrates, the bulk of the structure sits below the waterline, using submerged pontoons for buoyancy and stability. only a minimal platform breaks the surface. This approach is proven in offshore oil platforms, where semi-submersible rigs operate in some of the harshest marine environments on Earth. The key difference is motion damping. By placing most of the mass underwater, the structure's center of gravity drops below the center of buoyancy, creating a powerful restoring force. When a wave tilts the platform, gravity pulls it back to vertical. The motion still exists, but the period lengthens and the amplitude decreases to levels within human tolerance. The mechanism depends on precise ballast control. Semi-submersible platforms use pumps to move water between internal tanks, adjusting trim and stability in real time. Sensors monitor the platform's pitch, roll, and heave, feeding data to automated systems that redistribute thousands of tons of ballast within minutes. This is not passive floating. It is active structural response, requiring constant power and maintenance. A platform of this type can handle significant wave heights, but it cannot ignore them. The engineering trade-off is clear. You gain stability at the cost of operational complexity and energy consumption. For an offshore oil rig with a large crew and industrial-scale power generation, this trade-off makes sense. For a residential floating city, the economics become questionable. The cost of making a floating city survivable exceeds the cost of traditional construction by a factor of 3 to 5, depending on location and design. Kansai International Airport in Japan, built on a reclaimed island in Osaka Bay starting in 1987, faced subsidence issues and required continuous foundation adjustments, but the per square meter cost remained lower than equivalent floating infrastructure. Land reclamation produces fixed real estate that integrates with existing legal and utility frameworks. Floating platforms require redundant systems for power, water, waste treatment, and emergency evacuation, all of which must function independently of shore-based infrastructure. Insurance and regulatory approval add further expense. No international consensus exists on whether floating cities fall under maritime law, coastal development law, or some hybrid framework. This legal ambiguity delays projects and increases financial risk for developers and residents. A deeper problem surfaces when considering environmental impact. Ocean colonization has been criticized as blue colonialism, an exploitative extension of terrestrial development into marine ecosystems. Artificial structures disrupt existing habitats. Anchoring systems damage the seabed. Waste discharge, even when treated, introduces contaminants into sensitive areas. The common heritage of humanity principle, negotiated during international law of the sea discussions in the late 20th century, declares the ocean a shared resource requiring collective stewardship. Floating cities, particularly those operated as private ventures or micronations, challenge this principle by asserting exclusive control over ocean space. The comparison to space colonization holds here as well. Both frontiers raise sovereignty questions. Who owns a floating platform in international waters? Can it declare independence? The answers remain unsettled, creating both opportunity and conflict. Today, no floating city operates at scale in open ocean. Proposals continue, but construction lags behind ambition. The Palm Jumeirah in Dubai demonstrates that humans can build on water when sheltered by geography and supported by enormous capital investment. Its 5.5 million cubic meters of rock and 94 million cubic meters of sand created fixed land, not floating infrastructure, and it benefits from the relatively calm waters of the Persian Gulf. Efforts to replicate this model in exposed ocean environments have not succeeded. Japan's ocean spiral city remains conceptual. Smaller floating neighborhoods exist in protected harbors and coastal zones, but these are maritime extensions of land-based cities, not independent ocean settlements. They prove the technology works in limited conditions, not that it scales to the scenario the term floating city implies. The evidence shows that floating cities can survive a real ocean only under narrow technical and financial conditions. Semi-submersible designs with active ballast control can handle wave forces, but they require industrial engineering, continuous power, and maintenance regimes that challenge residential economics. Modular surface platforms offer flexibility but sacrifice livability. Underwater habitats avoid surface wave energy but introduce pressure, access, and psychological constraints. Each approach solves one problem while exposing others. The ocean remains hostile to permanent human settlement, not because the engineering is impossible, but because the cost, complexity, and environmental consequences outweigh the benefits when compared to available alternatives. Ocean colonization as a response to land scarcity and climate change is technically feasible. Whether it is practical, ethical, or sustainable is a different question, and current evidence suggests the answer depends more on law, economics, and ecology than on construction capability. The lesson is not that floating cities will never exist. It is that survival in open ocean demands compromises most people are unwilling to make. You can build a structure that floats. You cannot yet build one that makes the ocean feel like solid ground. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.